All right, so today I wanted to review this problem with everybody. So here we have basically a structure, solid structure, with a top width of W1 and a bottom width of W2, and the length is L. And we're going to apply a force, P. Okay, so we're going to pull on it. And I gave you some values for E, for W1, W2, T, L, and P. Okay, so what we're going to do is we can get to a solution, and then you could try to solve for it. So what we need to do in the first step in doing these problems is we're going to basically discretize the solution, or break it up into many pieces. Okay, so we have a node 1, a node 2, 3, 4, and 5. All right, we could cut it up into more. It'd be more accurate. Okay, but we can cut this up into many pieces. Here we have 5 nodes and 4 elements. Okay, so we can approximate these as a rectangle shape. Okay, which will give us a pretty close approximation. All right. And we can then make those solid structures into something that we can look at in terms of like a spring, all right, element, because they stretch like springs, just not as much. So we have element 1, element 2, 3, 4, and then we have the basically the deflection U1, U2, U3, U4, and U5 at the nodes. All right, so what we're end up going to do is we're going to solve for the displacement at each one of those nodes. And if you made more nodes, you would just have a bigger matrix of displacements. Okay, so I did over here on the right here. This is a free body diagram at each node. Okay, so you have a reaction force at the top, and then here, because it's like a spring, okay, we kind of cut it in the middle of the element, and you have this force right here, K1 times U2 minus U1. And then same with, if we looked at element 2, we cut it, and sorry, node 2, element 1, you would have an equal and opposite force here, which is the same. All right. And we go through node 1, 2, 3, 4, and 5, and you see that these are all the forces acting on each node. And again, it's U, like if we go up here, let's look at this one. It's U3 minus U2. It's because we look at how much that element now stretches. Because if U3 goes down 5 and U2 goes down 2, then really this is now stretch 3. All right, so again, let's review and then we'll get to more. So we have this surface, and we're applying we have this solid structure. We're pulling down with a force P, and we want to find the deflections. So we cut it up into a whole bunch of pieces. We then do our free body diagram on each node, and we have forces. All right, so what are some of these equations, and how do we figure out what K is? Well, here, right here, this is a just telling you about what the strain is for one of these elements. All right, so this could be A2 or A3, whatever. And again, this sketch right here is just showing you you have your equivalent spring for that certain element, and we're applying a force. So some of the equations that we need to use, or you could find, is here's stress, here's strain, here's Hooke's law. We combine these equations and we can get this force AE over L times delta L, where KEQ, your equivalent stiffness, is AE over L for this particular structure. So here the force in each element is your equivalent stiffness for that certain element times delta L, which is U of I plus 1 minus U of I. All right. And we can keep going through all this and plug in what the equivalent K is. And because we're doing these rectangles, we're going to have to do an average area, which is it's just A of I plus 1 plus A of I over 2. All right. because we're just using an average area, all right, because of the shape. And so what we do is now we can find equivalent Ks. So you can find K1, K2, K3, K4, and K5. Oh, sorry, there's no K5, sorry. And at each node, sum your forces. And now we can put this into a matrix form because it's easier to use it, look at matrices to solve for these displacements. Okay, so we have our stiffness times our displacement equals our load matrix. So what you need to do is these equations here, you're going to split apart so you get this matrix. All right, and when you multiply the top row to these sections here, it equals R1. All right, that's why if you look here, this equation here comes from this first row times these, it equals that. All right, so I'm just going to backtrack. There you go. And after we have this matrix, what we need to do now is we need to apply boundary conditions. So the boundary conditions, there's two things. U1, the deflection at the very top, at point 1 is 0. And then we have a load being applied at node 5. Okay, so we set the first row so it's 1, 0, 0, 0, 0. So therefore, if we multiply that through, we get U1 equals 0. And then we apply our load P. And then you can use your matrix division or matrix identities. Here you can do the -1 times this load matrix. So this K is this matrix. Oops. This whole matrix is K, and then this is your matrix B. So this is a method of using forces in free body diagrams, looking at all of the system. Well, the way we normally do this in FEM is we look at each element and we look at the forces acting on the element, and then we apply that for each element. Okay, so if we look at an element and we look at the internal forces, okay, we have basically a downward arrow, okay, and then an upward arrow. So we're kind of looking, if we go back up here, to these forces right here. All right. So those are the forces that are acting internally on the element. And if we add these two up, they should equal 0. And you could switch the top one to go up, but then you need to switch the signs here. And the reason why we do this is because I'll talk about this more, it makes the analysis and the derivation easier. Okay, so we're looking at the internal forces and of each element, and what we do is now we have two forces, f of I and f of I plus 1, all right, and for each element. So what we can do is we can put each element into a matrix, and now we have a stiffness matrix, okay, and we can then start putting these values of stiffness in certain sections. So for element 1, K1 goes here, negative K1, and K1. All right, these positives and negatives come from this equation right here. So like there's a positive value in front of UI and a negative value in front of UI plus 1. Okay, so if we take this matrix right here, so that states Fi equals, we take this, multiply by that, KEQ times U1, oh sorry, UI, and then we multiply this one by that one, minus KEQ times UI plus 1, which should give us the top equation. And if you're looking at element 1, you can then put these. Okay, and so here we have the stiffness matrix for element 1 going in these 4 cases. And then we do each element and we add to this matrix to get this big stiffness matrix. So if you notice here you have K1, here you have K2, here you have K3, and then here you have K4. So it builds the matrix that way for each element. All right, and if you go back up here, what we're doing is we're doing it for each element, but the basic line is you have your force equals your stiffness, equals your stiffness, which is K, equals your displacement values. All right, so in bottom line, you have stiffness matrix, K, you have your deflections, U, and then you have your load matrix, which we'll call B. All right, or forces. Okay, so again, forces equals your stiffness times your, you have forces times stiffness times your displacements. And that's what we have down here. Your K, which is your stiffness, your displacement, and your load, or your forces. And here I just simplified. We could have had another matrix before this, but I've already applied the boundary conditions to this first row and to this value here. And you get the exact same equation that we had above, but using the elemental method of FEM, where you just look at each element and then build your stiffness. And you can then use, again, do this, and you can get those solutions. All right, I hope this makes sense, and thank you.